Welcome to today's paper reading. Today's paper is titled, Large Language Models as an Indirect Reasoner, Contrapositive and Contradiction for Automated Reasoning. This paper was published on the AR14 preprint by Yanfang Zhang and colleagues from Nanjing University of Science and Technology and other institutions. The paper addresses the challenge of improving the reasoning capabilities of large language models, LLMs. It identifies that previous methods, such as chain of thought and self-consistency, which follow direct reasoning, DR, frameworks, struggle with many real-world tasks. To address this, the authors propose a novel indirect reasoning, IR, method that employs logical contrapositives and contradictions. This method is designed to enhance LLM's ability to perform tasks like factual reasoning and mathematical proofs. The methodology involves two key steps: leveraging logical equivalents to augment data and rules, and designing prompt templates to trigger IR based on proof by contradiction. Experimental results demonstrate significant improvements: a 27.33% increase in factual reasoning accuracy and a 31.43% increase in mathematical proof accuracy, compared to traditional DR methods. Notably, combining IR with DR yields superior results, highlighting the effectiveness of the proposed strategy. The introduction of this paper highlights the success of pre-trained large language models, LLMs, in various tasks such as language comprehension, content generation, and logical reasoning. These models excel due to their ability to infer from context in a zero-shot or few-shot manner, allowing them to generalize well to unseen tasks. Among these abilities, reasoning is crucial for determining the performance of LLMs. To enhance this reasoning capability, the authors propose the use of chain of thought (COT) prompting, which encourages LLMs to explain their reasoning processes, often leading to improved results. Additionally, the paper introduces indirect reasoning, IR, as a method to overcome the limitations of direct reasoning, leveraging principles of logic equivalence such as contrapositive and contradiction. This approach is designed to be simple and can be integrated with existing direct reasoning methods, potentially further enhancing the reasoning abilities of LLMs. Figure 1 illustrates the application of indirect reasoning using large language models, LLMs, in zero-shot and few-shot learning scenarios for complex problems involving mathematic proof and factual reasoning. Traditional direct reasoning methods struggle with these tasks, but our proposed method leverages the logical principles of contrapositive and contradiction to guide LLMs, leading to more accurate reasoning and successful deductions to correct answers. This approach significantly improves the accuracy of LLMs in these challenging tasks. The research on improving the reasoning abilities of large language models, LLMs, can be broadly categorized into three main approaches. First, fine-tuning methods aim to enhance reasoning through supervised fine-tuning, often requiring manual labeling of reasoning processes, which can be labor-intensive and may lead to the problem of catastrophic forgetting. Second, tool-based methods propose using external tools to augment LLM capabilities, including integrating real-time knowledge and external information through methods like Retrieval-Augmented Generation, RAG. Lastly, COT-based methods utilize prompts to help LLMs better solve reasoning problems, employing techniques such as zero-shot and few-shot COT, and enhancing performance by selecting optimal examples or incorporating external information. These methods collectively aim to address the challenges LLMs face in complex reasoning tasks. Figure 2 illustrates the fundamental concepts involved in factual reasoning. It highlights the roles of facts, F, rules, R, answers, A, reasoning processes, P, questions, Q, and intermediate conclusions, intercon, in the reasoning process. Understanding these key notions is crucial for grasping how factual reasoning operates within the context of logical and mathematical proofs. Figure 3 illustrates the framework of our proposed method, which is divided into two stages: rule augmentation and indirect reasoning. In the first stage, the method prompts large language models, LLMs, to augment the rule set. This augmented rule set, along with the given facts and questions, is then used as input in the second stage to implement indirect reasoning with LLMs. This approach aims to enhance the reasoning capabilities of LLMs by combining direct and indirect reasoning methods. In this section, we introduce the preliminary knowledge necessary for understanding our method. We discuss two methods of indirect proof, the contrapositive method and the contradiction method. The contrapositive method is based on the equivalence of an implication and its contrapositive. For example, PQ is equivalent to QP. The contradiction method, praised by mathematician G.H. Hardy, involves assuming the negation of a statement to derive a contradiction, thereby proving the original statement. Additionally, we explore how large language models, LLMs, can perform factual reasoning in natural language, which is similar to mathematical proofs but with predefined fact and rule sets. The methodology presented in this paper is divided into two main stages: rule augmentation and indirect reasoning. In the first stage, rule augmentation, the authors utilize the equivalence between the contrapositive proposition and the original proposition to generate additional rules. This is achieved through a few-shot prompt template that helps large language models, LLMs, understand and apply these augmented rules more effectively. The second stage, indirect reasoning, involves the use of explicitly designed prompt templates to facilitate reasoning processes. These templates include zero-shot and few-shot approaches. Zero-shot templates provide detailed instructions to guide LLMs without the need for labeled examples, while few-shot templates include intermediate reasoning steps based on similar examples. Both types of templates are designed to suit different scenarios and to help LLMs perform reasoning tasks accurately. The methodology also emphasizes the importance of including diverse examples in the prompt templates to ensure comprehensive reasoning. In this section, the authors propose a direct-indirect reasoning (DIR) framework that combines indirect reasoning (IR) with direct reasoning (DR). This combination aims to enrich the reasoning paths available for solving complex problems. Various techniques exist for aggregating the results of multipath reasoning, such as selecting the most commonly occurring results, or utilizing the law of probability of the outputs. In this paper, the authors employ a voting process to select the most frequently occurring results. The voting process is mathematically formulated, involving an indicator function and the number of candidate answers. In cases of conflicting voting results, the authors use large language models, LLMs, to determine which reasoning is more reliable, with the relevant prompt template provided in Appendix A. In this empirical study, we evaluate the effectiveness of our proposed indirect reasoning (IR) method using several key metrics. These include the accuracy of the answer (A), the accuracy of the reasoning processes (AP), and the overall accuracy (OA). We implement our method using popular COTI-based prompt methods and the self-consistency approach, with specific temperature settings for GPT 3.5 Turbo and Gemini Pro. We verify the effectiveness of IR through factual reasoning tasks and mathematic proof tasks, comparing its performance with direct reasoning (DR) methods. The results show that IR significantly outperforms DR in various scenarios, demonstrating its superior reasoning capabilities. Table 1 presents the reasoning accuracy of various methods on the proof math dataset. Key metrics include answer accuracy (A), reasoning process accuracy (AP), and overall accuracy (OA). Notable performances are seen in GPT 3.5 Turbo with AA at 88.57%, AP at 80%, and OA at 77.14%. Gemini Pro shows AA of 77.14%, AP of 65.71%, and OA of 60%. The self-consistency IR method stands out with AA at 97.14%, AP at 88.57%, and OA at 85.71%. Table 2 presents the reasoning accuracy of various methods on the proofwriter dataset. Key points include the performance of GPT 3.5 Turbo with direct reasoning (DR) at 46.67% and indirect reasoning (IR) at 58.67%, and for Gemini Pro, DR at 78% and IR at 76%. The self-consistency method shows DR at 42% and IR at 70.67%, highlighting the effectiveness of indirect reasoning across different models. Table 3 presents the reasoning accuracy comparison of direct reasoning (DR), indirect reasoning (IR), and direct-indirect reasoning (DIR) frameworks on the proof math hybrid dataset. The results show that DR achieves the highest accuracy across all metrics, A, AP, OA, compared to DR and IR, indicating its superior performance in handling hybrid reasoning tasks. Table 4 presents the reasoning accuracy comparison of DR, IR, and DIR methods on the ProofWriter hybrid dataset. The data shows that DR achieves the highest accuracy in AA, AP, and OA metrics, indicating its superior performance in handling hybrid reasoning tasks. Specifically, DR scores 51.33% in AA, 17.67% in AP, and 17.67% in OA. IR scores 45% in AA, 28% in AP, and 26.67% in OA, while DR scores 58.67% in AA, 33.67% in AP, and 32.67% in OA. These results highlight the effectiveness of the DR framework in improving reasoning accuracy across different metrics. Figure 4 illustrates the impact of rule augmentation on both DR, direct reasoning, and IR, indirect reasoning, methods, as measured by the overall accuracy, OA, metric. The results show that rule augmentation generally enhances the performance of both DR and IR, thereby improving the reasoning capabilities of large language models, LLMs. Specifically, in tasks involving factual reasoning, the augmentation of rules has a significant positive effect on performance. However, this effect is less pronounced in tasks related to mathematic proof, possibly due to the fewer rules involved in such problems. Figure 5 illustrates how inference rules, IR, significantly reduce the number of reasoning steps required to reach a conclusion in mathematic proofs. This efficiency is crucial as it not only speeds up the proof process but also decreases the likelihood of errors, making IR a superior method compared to direct reasoning, DR, in such tasks. Figure 6 illustrates how indirect reasoning, IR, enables large language models, LLMs, to reach conclusions in factual reasoning tasks with fewer steps compared to direct reasoning, DR. This reduction in steps is attributed to IR's ability to streamline the reasoning process, thereby decreasing the likelihood of errors. The figure also highlights how DIR, direct and indirect reasoning, can better stimulate the reasoning capabilities of LLMs by enriching their reasoning paths and encouraging the use of both DR and IR. This dual approach not only simplifies complex reasoning scenarios but also enhances the overall reasoning efficiency of LLMs. In this paper, the authors propose an indirect reasoning method designed to enhance the reasoning capabilities of large language models, LLMs, through tailored prompts. This method effectively addresses problems that cannot be directly derived from known conditions and rules. The effectiveness of this approach has been validated in both factual reasoning and mathematical proof tasks, demonstrating its utility. Looking ahead, the authors suggest exploring the integration of more complex logical laws to further improve LLM's reasoning skills. The work also highlights the broader impact of this method, which can expand the application scenarios of LLMs and inspire better use of AI technology. However, it is noted that the method may inherit the limitations of existing LLMs, potentially leading to incorrect or biased answers that could negatively impact various applications. Thank you for watching.